Thank you very much for enabling me to give this talk. I will be talking about caustics, and I will be basically interacting with many of the previous talks, including Oliver Hans and Christophe Pichon's talk. So let's start with the most elementary understanding of our cosmic web. So this is a two-dimensional embodied simulation, dark matter only, very cheap. And the most important thing is that what you see is that during structure formation, you develop multi-stream regions. So that's something which you all are very familiar with. And the only thing I wanted to say about this is that the boundaries between the single and the triple, or the single and the higher image regions, or stream regions, I should say, in large-scale structure, these are bounded by so-called fault caustics. So the fault caustics are the places where you have shell crossing and where the deformation tensor becomes singular. And what you can see here in 4 different slices is that you have at the very top, you have a very early slice where everything is still single stream. Then you see the first Seldovich pancakes forming, bounded by these shell crossing regions, which I call it in red, which are the fault caustics. And as the simulation evolves, you see that the structure of the cosmic web, which by eye you would characterize as the geometry of the cosmic web, is nicely captured by these caustics. So this is fault caustics, which is the first order caustics. What I will do in this talk, I will extend that to higher order caustics and show how that relates to the cosmic web and how we can use this to probe the cosmic web in novel ways. So the study of caustics goes way back. So it was developed by René Thom and Vladimir Arnold in a general classification of degenerate critical points. Then Arnold, together with Seldovich and Sergei Shandarin, showed that you can use this to classify the cosmic web. And this was usually successful in the fact that people could try to anticipate what the cosmic web was going to look like without having to run embodied simulations. However, there's one big drawback, is that this paper, part 1, the 1982 paper, is only two-dimensional. And unfortunately, they couldn't go further and do the three-dimensional one. So this is something we recently managed to do, which I will talk about a little bit. So first, to think about what is a caustic and how should I think about this, I will be talking about Lagrangian fluid dynamics, meaning that you describe the evolution of the cosmic web with a Lagrangian map. So what you say is xt is the position of a particle which started at q and it got a displacement s. And what you can do in Lagrangian fluid dynamics, which you're probably very familiar with, is you can say, well, the density at a certain Eulerian position in your embodied simulation is the sum over the different streams. And what do you sum over? Well, you sum over the mean density divided by the Jacobian. So the Jacobian of this Lagrangian map, which turns out to become the gradient of x, and you take the determinant, and of course you take the absolute value, because as the streams are turned inside out, the Jacobian becomes negative. You don't want to include negative density, so you take the absolute value. And the key points, which I will repeat over and over again, is that you can take this deformation tensor, yes, the gradient of S, and you can calculate its eigenvalues, that these are the mu's, and you can calculate its eigenvectors. And I will show how the interplay of these are important for the higher order caustics. So one thing to realize is that density spikes when 1 plus mu is 0. So in terms of the growing mode, in the Seldovich approximation, it's 1 minus the growing mode of B, the growing mode times the eigenvalue of the eigenvalues of the Hessian of the gravitational potential. But if you want to go to higher order caustics, you will have to include the eigenvector fields. So what we did in order to go to the three-dimensional cosmic web and develop this framework mathematically rigorously is to say, well, let's take Lagrangian space. So that's the left. Yeah, here Lagrangian space. And let's draw an arbitrary manifold in here. So let's say the line C in this case, but in 3D it could be a two-dimensional manifold. It can also be the whole space. What you now can do is you can map every point on this manifold to a Eulerian space using this map X. And what happens at the caustic is that you develop a non-differentiable point. So this point QS gets mapped to this non-differential point, so you get a kink in the curve. This is what it means to be a caustic. And the interesting thing is that what you can do is you can derive an if and only if condition for this to occur. And what you will find is that you need a tangent vector t in the space at the tangent space at QS. And what you need is that for all I, being 1, 2, 3 in 3D, 1 plus the eigenvalue field times the dual of the eigenvector field inner products with this tangent vector has to be 0. If this is the case for all I, if you can find such a tangent vector, then you have a caustic. If not, you don't. So the first thing to realize that if you take the whole space, then you are completely free to choose your tangent vectors. And it's enough for 1 plus mu to be 0 for 1 I, because you can always take your tangent vector in such a way that it's orthonormal to the other eigenvector directions. So this is how you can derive the fold manifold. So you see indeed that you get A2, which is the fold caustic, is all the initial position points, Q, for which 1 plus mu is 0. And this is very trivial because if you look at the density fields, you divide it by the product of 1 plus mu, the eigenvalues, and for that reason, AT2 corresponds to shell crossing. But now it becomes a little bit non-trivial. If you now apply the same condition to this A2 manifold, then the eigenvector becomes important because the tangent space has been reduced because you have dropped 1 dimension. And you find that the cusp caustic, which corresponds to the red line developing this kink like this, the blue line is the cusp caustics in this case, is the case where you have shell crossing at a certain time. And in addition, you have that the directional derivative of the eigenvalue field in the direction of the eigenvector field is 0. So if you now apply the same condition to this cusp manifold, you can go down and down and down till you have exhausted all the caustics. So you can also basically prove catastrophe theory in the Lagrangian fluid dynamic setting in this way. And what you find is that you have these fold manifolds, you have these cusp manifolds which involve the eigenvector fields. You have the swallowtail caustic, which includes the second order derivative. You have the butterfly caustic, which corresponds to points, which have a third order derivative in the eigenvector field. And in addition, you find that there are these umbilic points, which are the places where 2 eigenvalue fields are identical to 0, or, well, coincide, let's say. And these are all the caustics which you can see in embodied simulations which are stable. So that means that you could artificially generate higher order caustics, which are not realized in embodied simulations because these are unstable and these are generic caustics. So the important thing to note is that these different caustics, this is something which already was realized by Arnold in the 70s, can be associated to different elements of the cosmic web. So we had the fold caustic, which corresponds to collapsed regions of shell crossing. You have the cusp caustic, which corresponds to walls in a 3-dimensional simulation. You have the swallowtail caustics, which correspond to filaments. You have the butterfly caustic, which correspond to clusters. And surprisingly, you have 2 additional caustics, the D4 and the D5, which also correspond to filaments and clusters. So according to catastrophe theory, you have 2 types of filaments and 2 types of clusters with different formation histories. So what we now can do is we can draw some conclusions from this general classification. The first thing is to note that even though structure formation is often described in terms of the density perturbation, the initial primordial density perturbation, or the gravitational potential, catastrophe theory is really talking about the eigenvalues and the eigenvector fields. And one surprising thing is that if you take a density perturbation, calculate its gravitational potential, calculate the Hessian at every point, so this is still in 2D, and you calculate the eigenvalue fields, so that's the left one and the right one, you get this filamentary pattern. So the eigenvalue fields are highly non-Gaussian, and these are basically already the proto-filaments, so to say. So indeed, everything is encoded already, or a lot is encoded in the initial conditions. You can see the filament already in the eigenvalue fields of the primordial deformation tensor, which is rather nice. So what you now can do is you can take, again, the same embodied simulation, but in addition I will do the Zeldovich approximation. So in the left you should see the Zeldovich approximation, on the right you see the embodied simulation, which is just corresponding to the same initial conditions in the time. And of course, the Zeldovich approximation has broken down at late times. because it's going all over the place, and the density estimate would be ridiculous. However, what we can still do is calculate the caustics of the Zeldovich approximation and lay them on top of the embodied simulation, because the caustics are the places where the Zeldovich approximation starts to break down, because these are the locations where shell crossing takes place and nonlinear evolution really kicks in. So what we can do is we can take the primordial density perturbation, we can calculate the caustics corresponding to the Zeldovich approximation, and you get this pattern on the left, which is an embryonic skeleton of the cosmic web, which we call the caustic skeleton. You can see the red lines, which are the fault caustics, which are shell crossing regions at a certain time. In addition, you see these blue lines, which are the cusps. In 2D, that corresponds to the filaments. And you have all these points, which are the maxima and the minima of the eigenvalue fields, which correspond to the merger and the creation of these multi-stream regions. If you now take this skeleton, which is plotted on top of the eigenvalue field, the first eigenvalue field of the primordial deformation tensor, and plot them on top of your embodied simulation, you see that everywhere where you by eye would identify a filament, you get a blue curve, and indeed these multi-stream regions are bounded by these red curves, which are the faults. So you see that even though the Zeldovich approximation has broken down at late times, you can still retrieve information about the geometry of the cosmic web from the caustics of the Zeldovich approximation. Of course, the whole formalism doesn't depend on the Zeldovich approximation, but it's a very nice first order approximation to get started. So you can do this in 2D, but you can also do it in 3D, where you see the time evolution and you see that the caustic skeleton is growing. So in this case, the red is the surface and the density field is a density estimate of an embodied simulation. And you see that you have the first development of Zeldovich pancakes, which then extend to form this very interconnected cosmic web. You can also see it in an embodied simulation where I've rotated the box. So the left is an embodied simulation. It's actually Noah and Libeskind simulation, which was used for the comparisons of different cosmic web identification schemes. The central figure consists of filaments. So you see the blue, that's the A4 filaments, and the red, you see the D4 filaments, which are forming at different formation times. And the one is more stocky and the other one is more elongated. And on the right, you see the same embodied simulation, but now with also the membranes, the walls, the cusps in there. You see that these caustics very nicely trace the geometry which you by eye would recognize in such an embodied simulation. So what can we do with this? One thing which we would like to do is use this to describe the topology of the cosmic web. So in the interest of time, I will go very quickly through this. So you take your primordial density perturbation, you can calculate its eigenvalue field, and you can consider super-level set filtrations of that eigenvalue field, which is on the top figure, and that corresponds to the time evolution of your embodied simulation, or your Zeldovich approximation. So the main point is that these red curves correspond to the red curves here in the Zeldovich approximation and the embodied simulation. And what you find is that at mergers, for example, at this saddle point, these two different multi-stream regions have merged. So rather than studying the critical points of the density perturbation, Lagrangian catastrophe theory seems to imply that we have to look at the critical points of the eigenvalue fields of the primordial density perturbation, which is kind of an interesting twist. Currently, we are investigating how we can try to track the topology of the cosmic web using this formalism by studying the eigenvalue fields in more detail. And I would like to highlight that the PhD student, Erich Wilding, has done this in 2D, and Joni Slansky is currently doing this in 3D, which is really nice. So because of time, I will want to show one last thing, which is that these caustic conditions are really nice and concise. However, they are very non-linear. So if you want to put flesh on the bones of this caustic skeleton and study it in detail and see what the density field and the galaxies around these caustics do, it would be really nice to have a constrained Gaussian field theory formalism which deals with this. However, the Hofmann-Rieback algorithm only works for linear constraints because it relies on the fact that the residue is independent of the constraints which you are imposing. However, recently, I managed to extend linear Gaussian random field theory or linear constraint Gaussian random field theory to nonlinear Gaussian random field theory, where what you do is you consider a space which corresponds to your nonlinear constraints in the space of a set of linear constraints. So for example, if you want the eigenvalue fields, then you have to describe the second order derivatives of the gravitational potential, and then the eigenvalue field is a nonlinear function on this space. If you now want to impose a condition on this, you can first sample this small space, which you can do with, for example, a Hamiltonian Monte Carlo sampler. And then you can input that in your Hofbauer-Rietveld algorithm to sample the unconstrained, the constrained Gaussian random fields imposing these nonlinear constraints, which is really neat, because now we can put these caustics in the constraints. So this is, for example, the mean field of a cusp caustic, where you see the Zadovich pancake come out. Here you see the swallowtail caustic. If you look at the umbilic caustics, then there is a threefold symmetry which is built into the algebra, which is not manifestly apparent when you just write down the formulas, but it turns out that this linear algebra leads to this kind of mean shape where you see that different filaments start to merge. And finally, what you can do is you can do this in 3D, and here what you can do is you say, well, let me build a simulation for which you have the formation of a wall, so that's a cusp, at the center of the embodied simulation forming at a certain growing mode at a certain length scale. So you have basically a few quantum numbers qualifying this one wall. And here you see the red point where I've imposed these constraints. You see that's indeed a wall because you have here this line-like structure in 2 slices, and you have a kind of a plane where you go through the structure like here. If you now run an embodied simulation on the same initial conditions, then you see indeed that you get a filamentary or a line-like structure here and there, and here you get a plane-like structure, and you have realized this cusp in your embodied simulation. And here you see it in a few slices. You can also do it in 3D, where if you look carefully, then you really see that the red surface is at a place where you optically, by looking at the density, would place the wall. So it's a very neat classification of the cosmic web based on the formation history. Finally, I would like to show this movie where I've done the same thing, but then for a filament. And you see that there is a filament constraint in the middle. And you see that it becomes a bridge between very dense clusters. These clusters are not put in the simulation using constraints. It's a consequence of the existence of this filamentary structure that you get these clusters out of the simulation. So with this, I would like to conclude. I would like to have shown that caustic skeleton theory can be developed in 3D using very elementary mathematical tools. It classifies the different elements of the cosmic web based on the formation history rather than the morphology we see today. It doesn't have any free parameters. Everything has nicely interpretable quantities. It predicts the existence of 2 types of filaments, which is interesting and which is something we are currently investigating, which form at different formation times and have different formation histories. And by studying Gaussian random field theory, with Zeldovich approximation, with caustics, you see that the eigenvalue fields play an important role. And we are currently in the process of investigating the statistics of, for example, the critical points of eigenvalue fields of Gaussian random fields. And the question is, to what extent can we understand the nonlinearity of the current cosmic web from the eigenvalue fields, which are already non-Gaussian by themselves? So with this, I would like to thank you for
Any question? Ravi?
Thanks. That's beautiful. So you showed a comparison between the Zeldovich caustics and the simulation. And,
this one.
No, a little earlier, where the Zeldovich was kind of fuzzed out and the...
2D or 3D?
Yeah, something like that one. Just the next one. Oh, yeah. Now, people had also worked with the adhesion approximation.
Yes.
How well does I guess that's better than Zeldovich, but is there a reason to not have shown that?
Yes, so I didn't run these simulations, that's the first reason not to show it, but the real motivation is that by defining these caustics on the Zeldovich approximation, where things start to break down, everything is still local in Lagrangian space. So the calculations are really simple because you only need the derivatives and the values at a certain position. So it's very easy to define these elements. If you would go to the adhesion model, then it becomes non-local in initial condition space. And that makes the analysis a lot more tricky. So you can do it, of course. But for example, if you would like to calculate the statistic, like the Rice formula and statistics of critical points, then it becomes very complicated to do. The other reason is that if you use pure Hamiltonian dynamics, then catastrophe theory applies. When you are not doing non-Hamiltonian dynamics, like you have in fixed causality, then things become more subtle, and the classification of the caustics doesn't necessarily apply anymore.
Thanks.
Any other question? Oliver?
So I also have a question about exactly this one. So I guess what this tells us that basically Zeldovich is quite good to predict the collapse time of the first axis.
Yes.
But probably there is no way to get at any agreement for the second axis as well, because we know that Zeldovich clearly is wrong. Have you any thoughts about that?
Yeah, so we looked into that, but only very coarsely, so this is all work in progress. So we found that if you look at the critical points of the second eigenvalue fields, then these seem to be very correlated with the clusters of your cosmic web. So I completely agree that it will break down at some point, but it seems to extend a little bit further than I initially expected. So there is still some information in the second eigenvalue.
But given that you're already smoothing at the right scale in some sense.
Yes.
Yeah.
So in the last part where you talk about the constrained realizations, so I guess my question is, how far can you push this before it would be a violation of, say, so I understand you're probably putting in specific phases in the initial conditions to create the structures that you want in the late times. Is that correct?
No, so what we do is you can say, well, let's say that you want to form a wall at that length scale at that formation time. Then you first can calculate what is the likelihood for that to occur in an unconstrained Gaussian random field. And then if you are happy with this confidence, you say, oh, it's likely enough, then you can just impose that constraint in your embodied simulation, in your initial conditions.
So that comes in the phase and
what do you mean with phase?
Well, it has to be a Gaussian random phase. I mean,
well, the resulting distribution. So if you have a Gaussian random field, you have a linear constraint, and the resulting thing is again a Gaussian random field. If you have a Gaussian random field and a nonlinear constraint, then the resulting thing is no longer a Gaussian random field. It's a constrained Gaussian random field, but the fluctuation, the residue is no longer Gaussian.
okay.
Yeah, very nice. Can you comment about these two types of filaments and two types of nodes that you find?
So the one is the one you are completely familiar with, I assume, where you have two eigenvalue fields equal. So that basically means collapse in two regions, two directions, and that's the traditional filament which we are familiar with. But these other filaments, which is the swallowtail filaments, happens due to development of kinks. So they can be related to a single eigenvalue field. So they are really different. We are still in the process of seeing how these are realized in embodied simulations. So it's still very much ongoing work. And that was basically the motivation to develop this nonlinear constrained Gaussian random field theory. Because then you can just generate an ensemble of 100 of them. And you can stack them, and you can orient them, and you can check what are the statistical properties in the late-time universe for these different filaments.
And you have the same also for nodes, no? The fold and the umbilical caustic.
Yes, indeed.
So,
Yeah.
I guess I have two questions. Are you considering the fields beyond its second derivative, or are you limiting the description of the field up to its second derivative? Does my question make sense? Or?
So it depends on the caustics you are imposing. So if you want to have the fault caustic, then you only need the second order derivative of the gravitational potential. But if you want to have the cusp caustic, then you already need the third order derivative.
Because from my souvenir or remembrance, if you impose the field to be described only up to second derivative, the number of ridges you can pass through a given extremer is limited, right? Because it has to be ellipsoidal locally, right? Do you suffer from the same artifacts, or?
I'm not quite sure. I would have to think about it.
I saw in some of your plots that sometimes you had these blue lines, and there was another blue line which was trying to connect, but instead of connecting, it did this.
Yes.
This seems to be an artifact of the level at which you Taylor expand the field, so that locally you can only have one blue line. No?
I don't think it's a numerical artifact in that way.
Okay.
It's not,
well, not a
integral
numerical
line.
as in an error, but it's at the order. And my other question was, why do you want to consider the critical points of the eigenvalue field and not the potential or the density? Or
because these really correspond to the merger events of multi-stream regions. So if you have a maximum of the eigenvalue field, that's the creation of a Zeldovich spin cake. If you have a saddle point of the eigenvalue field, that's the merger of two multi-stream regions.
Okay. Okay.
So it has a very physical geometric interpretation.
Any other question? If not, I have questions. So I just wonder whether this caustic-based scalar method can account for the generation of vorticity around the caustic or the spinning of filaments themselves?
That's very much an all-open question.
Okay.
I would like to investigate that, but well, again, that's one of the benefits of having these constraint simulations is that you can easily do this.
Okay.
Because even though the formalism is very clean mathematically, implementing it numerically is very tricky because eigenvector fields are only line bundles, meaning that they don't have a direction, they only have an orientation.
Exactly, yeah.
So the numerical schemes become very tricky to implement. You have to do everything from scratch. So that slowed down the process a lot. But if you can generate them using these constraint simulations, you can make a lot more progress because you have a lot more control.
Okay, thank you. We are out of time, unfortunately. Maybe just a quick, if it's very quick. No.
Now I've forgotten what I was going to say. It was very pithy, but what? Oh, yes. Unfortunately, I'm going to ask you the obvious question. How can you apply this stuff to the data sets that are coming?
That's a very good question. So there are multiple answers to it. I will keep it very shortly. So these caustics are really a formation history. So it's a description of the formation process. And of course, in the data, we only have the distribution of galaxies at the current time. So there are basically different ways to go about it. You can do constrained realizations of the local universe. So that's something we are currently doing. We also have a hope to use maybe machine learning to recognize the different features in real data. That's, of course, a big drawback of using a scheme which depends on the formation history. It's very well suited to embodied simulations, less to redshift surveys.
Okay, let's thank Job again.